Very excited again to announce our next speaker. Professor Jeannette Bohg is at Stanford University, where she runs the, so sorry, catching my breath, where she runs the Interactive Perception Robot Learning Lab. Jeannette and her group have contributed to a very, very wide range of topics on imbuing robots with human-like sensor motor coordination, in particular imitation learning and learning from demonstration, as well as classical task and motion planning, and very relevant to this workshop, using LLMs and VLMs as components in the task and motion planning pipeline. So today, Jeannette will be telling us how to mobilize a manipulation molecule and with HDMI light sets. Go ahead. Thank you very much.
Hi, everyone. Quick question. Do I also need to put the mic into my computer? So that the people... Oh, okay, perfect. Okay, yeah, hi, everyone. Thank you very much for the invitation and also for the nice introduction. And today I wanted to talk about task and motion planning for mobile manipulation. And so maybe the first question you may ask yourself is like, what's the difference to just doing manipulation? I mean, is there really a difference? Do we need to think about it differently at all? And so that's what I want to propose today, that maybe we do need to think about it a little bit differently. And so let's get started. So first of all, I wanted to mention a little bit that in my lab, we've actually done a whole line of work on long horizon planning in the real world through task and motion planning methods. And here's kind of how we see, let's say, a very abstract version of a system that we would need for doing this kind of long horizon planning in the real world. So you have task planning that feeds into motion planning, that feeds into a reactive planner, which changes the environment. And then finally, through perception methods, these methods are basically, or these blocks are basically informed to do the right decisions in a loop. And TAMP, task and motion planning, really lives between the task planner and the motion planner. Okay, so now for the young people among us, I thought, okay, everyone is talking about system 1 and system 2 these days for some reason. And I thought, okay, let me ground in this slide what system 1 and system 2 is, maybe just for the young people among us, or for the much older, more senior people. So I would say like TAMP is the system 2, right? Like where you have this deliberate planning and thinking happening, and then system 1 is really the reactive part, the one that is actually lower in this kind of architecture that I'm showing here. Yeah. Okay, so this is just for grounding the discussion a little bit. There's always new terms invented to describe the same thing over and over again over the decades. That's what I learned after being in this field for a while. So I thought I put this translation a little bit. And so now let me like quickly walk through all the things we have done in this pipeline, right? Like so in 2019, we basically started thinking about how to make TAMP actually work in the real world by making it reactive and very adaptive. And so we proposed this object-centric TAMP method that actually more tightly connects the motion planner and the reactive controller. I'm not going to go into detail of these works, actually. I'm just going to show you a few. Then we, for the task planner, we actually use a symbolic planner for this work. But we also published a work where we ground the predicates that are needed to by the symbolic planner through a very interesting approach through actions, so that the perception part can actually in real time feed into the task planner, so that on the task planning level, we can also do quick replanning as well. And then we started to, a bit later, to actually take this architecture and start ripping out traditional parts from it and replacing them with learning-based methods. So we started by basically replacing these low-level control policies by learned policies. So this was a work that was called Concept to Robot, where we learned a multitask policy that was conditioned on language at that point, and that could basically output a lot of different actions. But we hadn't yet connected it with the system 2, if you want, or with the high-level reasoning and task planner. And that is really what happened then in 23 for ICRA, where we did TAMP with learned policies as well, and really needed to plan over how learned policies are actually changing the environment and use that to plan long horizon tasks as well. And finally, we replaced the symbolic planner as well and replaced it with an LMM and connected it to this TAMP with learned policies as well to make it complete system. Okay, so this was just like a verbal tool through kind of the historical things or, you know, the kinds of work we have done in our lab on task and motion planning over the years. And so I don't want to talk about these works today, but I just want to highlight one thing. I really like all these works. I think they all have a very interesting contribution in themselves. But if you look at how we demonstrated them, it's always in tabletop scenarios, right? Like, so they can solve very interesting different tasks, but they are confined to this tabletop space where the robot has a limited workspace, which introduces some of the geometric complexities actually in the first place. But I would really like to, or I was really ready at this point to go beyond tabletop tasks. And so we started in my lab to work on mobile manipulation actually. So here you see like one example from our work that was called TidyBot, that was published at IROS and then later at Auro as well in a longer version, where a robot basically cleans up your house, basically tidies it up based on your preferences. And so you see that now this is still like a pretty simple pick and place task that the robot is doing, but it has to now decide in which containers basically all the different items are going. So it's not a very complex TAMP problem actually. It doesn't really matter in what order the robot picks up the items, but it's just an example for the mobile manipulation part. So we did a bunch of things with also multiple agents. And here, for example, we did mobile manipulation with two robots where we actually demonstrated, had a human actually demonstrating folding a small dish towel. And then the robots would learn an equivariant policy, and therefore they could do the same task of folding either clothes, folding or unfolding a piece of cloth at very different scales of the task as well. Okay, so maybe what you see is like these tasks are becoming more interesting, and potentially you could also think about the robot actually having to navigate through an entire house, through an entire office building, through an entire warehouse, maybe, to do all sorts of different manipulation tasks that have potentially difficult TAMP structures. But it also means that you have to decide when to do navigation, where you navigate to then execute an actual manipulation task, and how you coordinate the base and the arm actually. So today I want to focus on a work by these co-authors, and this one is about mobilizing your robot learning policy. And so basically what we want is, we want to reuse all the manipulation policy data that is already out there for different manipulation tasks that are actually happening, are basically happening very locally, maybe centered around one table or one shelf or something like this, but then chain these together with other manipulation tasks with maybe intermittent navigation that's happening. Okay, so how do we do this? So let's say we have some policy, let's say an image-based policy that is trained from a fixed or limited camera pose for a task like grabbing paper towels, like this one. So now it's not very useful if a robot can only grasp paper towels in a grocery store, right? Like from this particular pose. So the question is like, how do we make this policy runnable on a mobile platform that where maybe the mobile platform is starting from a new base position anywhere in this grocery store to actually drive up to this paper towel task. So what would happen is, so that's really what we want to do, like do this task even though we start from somewhere completely else. And the thing about these learned policies, especially image policies, is that they are very brittle when it comes to viewpoint change. So they're typically trained on data that is collected only from one viewpoint or maybe from a few ones, and then they're not very good at generalizing over it. So if you were to just naively navigate towards the paper towels and execute the policy from kind of a place that is maybe close to the paper towels, but not in the right space for the manipulation policy to actually work, it may result in this out of distribution initialization for the policy, leading to failures. So for example, on the left here, the robot gets too close and pushes the towel inward with the arm. And on the right, the suboptimal heading of the robot, so the orientation relative to the paper towel, makes the towel unreachable from the left arm. And so to handle these failures, one could improve, of course, that's the data collection point of view, right? Like the one thing you can do is you can just improve the robustness of the policy in different ways. For example, by just making data collection more extensive and basically you start collecting data from all sorts of different places to cover all the possible robot-based post and initialization in the scene for this particular task. That's, of course, pretty tedious. And so in this project, what we did is we actually kind of rethought the task a little bit and defined this new problem of policy mobilization, which aims to find the optimal robot pose that leads to an in-distribution viewpoint for executing the policy. Okay. So let's talk a little bit about prior work in just navigation, not necessarily for manipulation, actually. So prior work in the semantic navigation explores the setup where robots navigate to find specific objects in the environment. And methods for semantic navigation include classical SLAM-based methods and more recent learning-based methods, such as the ones shown on the slide. And these methods typically stop in an area where the object is visible and close, but they don't take into account what the manipulation policy is actually capable of and what is an in-distribution position for this policy. So we also, of course, here's again tidybot, right? But this work basically relies on primitives, so pick and place primitives, or actually tossing primitives as well that we had, instead of learn policy. And you know, actually the primitives that we had, they work pretty well, but there are definitely some objects where, you know, our predefined primitive is going to fail, unfortunately. So it would be really useful if it actually learn policies for these. Okay, and then we have methods like mobile Aloha as well that do mobile manipulation in an end-to-end neural network. And although this approach is kind of conceptually simple, it requires a lot of data if you want to make the policy generalized to all possible perspective and room layouts as well, right? Because this policy has been, for example, trained in the Stanford kitchen that we have there, right? And that's where it's going to work. And there are also methods that try to chain navigation with learned policies, but they typically assume that the initial robot poses of manipulation phases are known in advance, and they are not predicted, right? Like, so even if you go to a new place, the person who deploys the robot basically has to pick the spots from where the different local manipulation policies actually work. Okay, so we define this policy mobilization problem where we try to basically make robot manipulation policies that have been trained in these local areas easily runnable on a mobile platform. And formally, given Visuomotor manipulation policy Pi, trained with imitation learning on data recorded from one or a limited set of robot poses or viewpoints, we are interested in deploying Pi on a mobile robot in an unseen scene S. Okay. So now to study this problem of policy mobilization, we want to answer the following question. So what is the potential good policy mobilization approach? So I'm going to present one today. Can a given manipulation policy actually be mobilized? Mobilization, but and two methods of just like navigating too close to the object, for example, how well do they work? Do they even work at all? So today I will show you a novel method for policy mobilization. I will show you some metrics that show how hard or easy it might be to actually take a given manipulation policy and mobilize it. And we also, to study this whole thing, we also going to release a simulated task suite for evaluating these mobilization approaches. So if you're interested in this problem, I hope you can plug it into this suite and actually test it and evaluate it there as well. And we have several baselines that we evaluate in this suit as well for policy mobilization. Okay, so let's go to the first point of what we actually propose to do as a first way to kind of solve it, the first thing we came up with. So yeah, so first of all, here's like a wish list of what we want, right? So the policy mobilization approach needs to be aware of the environment in which actually the policy is going to be rolled out. It needs to be aware of what views and poses the policy can support. So somehow it needs to be policy aware. And sorry, these were the 2 points. And so here's an overview of the approach that I'm going to step you through. And it basically consists of 3 components. It consists of a Gaussian splatting model for rendering the scene from a specified view. It has a hybrid score function for estimating how likely a policy will be successful when executing from a given viewpoint. And we use Bayesian optimization for iteratively optimizing robot position and viewpoint. And in this work, we assume that the camera is fixed relative to the robot base. It's not like a movable or active head. And that means that sampling a robot pose also determines the camera viewpoint. Okay, so let's step through this a little bit more slowly. So first, we start with the manipulation policy that someone gave us, and we want to mobilize it. We want to put it on a mobile robot. We also assume we have all the training data that were used to train it. Then we collect RGBD images from the scene to train a Gaussian splatting model. So imagine the robot is being deployed in your kitchen, and it first makes like a little look around, basically, to see how this kitchen looks. Okay. And that allows us then to render novel viewpoints from any kind of viewpoint you can imagine, even not the ones that the robot hasn't yet, actually traversed as well. Okay, so next we define the score function that predicts whether a proposed robot pose that the robot is not yet in physically is suitable actually for running this manipulation policy that we want to execute. And this function considers 3 key factors. First, the viewpoint should be in distribution with respect to the observation in the demonstration data set. And the way we do this is actually by looking at clip features that we pre-computed on the training data, and now we compare the actual viewpoint that was rendered from the Gaussian splatting model with the training data and see how close it is, to see if it's actually in distribution with respect to the training data. We also found that we need to include some object detector that says like, okay, the target object that I actually want to manipulate according to the task I'm in, it has to be in the view. And third, the robot should not be in collision with the environment as well. So for that, we actually just used a point cloud that was reconstructed before from the robot actually driving around once in the kitchen. Okay, so with all of this together, we get the score function that tells us whether a hypothesized new pose of the robot would actually be useful to run this policy at all. And now we use the score function to guide Bayesian optimization, which iteratively samples new robot poses P, again, like not by the robot actually driving around, but in this Gaussian splatting model, to sample new robot poses to find the optimal pose that is in distribution for the manipulation policy and therefore has a good probability to actually succeed. Okay. So that's the method that we're proposing, and I'll show you how it performs soon. But I want to, as a part of this MobiPy framework that we are proposing, I want to show you also a few metrics that we use to actually evaluate how hard a given policy is to mobilize as well. So here are a few metrics for this policy mobilization scenario. So first of all, what makes this mobilization actually hard? So it turns out that one major reason that makes running a manipulation policy on a mobile platform hard is a spatial challenge, basically. So if you have a precise task, let's say you want to press a small button on a microwave, a 5 centimeter error or displacement during navigation might result in the robot actually failing, right? So you, especially for these very precise tasks, you want to actually place yourself, the robot should place itself pretty well. Okay, so to measure this spatial difficulty of a policy or the spatial challenge, we designed a spatial mobilization feasibility metric, a tongue twister. So the way we do this is we compute this by rolling out the learned policy a few times while perturbing the initial pose. So this can be in any, this can, by the way, be in any environment. It doesn't have to be in the test kitchen. And because the policy is trained on only a few viewpoints and environments, we expect the performance of the policy gets worse with this noise that is added. And the more it gets, we expect it to be worse, the more perturbation we actually add. And for manipulation policies whose performance drops fast with the scale of perturbation, it is also harder to mobilize this manipulation policy because it's really requiring you to drive to a very specific spot. So in this slide, there's just a few videos of policy rollouts in sim with base pose perturbation. And we noticed that for this particular, these two tasks, turning on the faucet and closing the door, you see that the policy performance kind of degrades, but it also varies across tasks, right? So on the top with the faucet, you actually have to be pretty precise to find this little lever, while the door is really big. So wherever you hit it, right, like it's basically going to close. So even with large perturbation, this closing of the door works pretty well, while the robot really struggles to basically turn on the faucet in all of these different kitchens, actually. Okay, so how do we now put a metric? Like we want a scalar value for this, right? Like to understand how hard it is to mobilize this policy. And to express this, we basically plot policy rollout success with respect to these perturbations. So in this plots here, you see on the x-axis, you see the scale of perturbation in centimeters. And then on the y-axis, you see the success rate. And so for closed door and turn on faucet, you see that it basically degrades, right? For this particular policy that someone gave you. And then you can find the perturbation scale or the centimeters of perturbation that make the success rate of the policy drop by half compared to when the policy is rolled out without any perturbation. So that you can think of this as the half decay time of the policy, right, if you want. And the smaller this value is, the more difficult it is to mobilize this policy because it requires really precise precision. Okay, so that's one of the metrics to, independent of any method, just analyze a given manipulation policy on how hard it is to put it on a mobile robot. Okay. So there's another metric that we found is actually quite significant because there's another challenge to make a given manipulation policy hard. So sometimes it can be hard to find a proper base pose to execute a manipulation policy because of a visual challenge as well. So for example, for this task where a drawer has to be closed by the robot, it is hardly visible even during training. So it's really hard to find a good angle towards this drawer if you don't even see it in your image, right? Like, so here is a way to visualize this for the different tasks we studied, where you see, like, for most objects, the object of interest is actually pretty well in view. But then if you look at the drawer, the second from the right, you see that you can hardly see the drawer. It's actually occluded by the robot itself, right? Like, so it's really hard to maybe mobilize this policy. Okay, so we also have the simulated task suite where you can actually, basically test these methods. It's based on RoboCasa, and we took basically 5 of the RoboCasa tasks and we evaluated in 5 unseen layouts while training on like many different layouts. We also included some baseline methods that are basically naive methods, right? Like, it doesn't matter what they are. Some of them are learning based, some of them are non-learning based, but they basically try to maybe drive up to an object or drive to a particular position that is given by natural language. Okay, so here's some results of this. So first of all, in orange is our method. The y-axis shows success rate, and the dashed line shows the best possible performance of the manipulation policy if it was started from the training position. So it's guaranteed to be in distribution. And here on the left of each bar plot, we see what happens to this policy if we started from perturbed versions, from 5 centimeters or 10 centimeters. And you see that the performance already drops And then we compare again to these baselines that are just driving up to the object of interest, basically, without being policy aware. So they don't take into account whether they are driving up to a place that is in distribution for this policy as well. So here are also some simulation results. I believe I'm out of time. Couple of minutes. Okay. Thank you. So here's some simulation results where you kind of see the final positions of the baseline versus our method that is pretty, converges pretty well to a good position. And then we also evaluated this on real robot tasks. So here you have the poor tomato task. Basically, you see the robot actually has to move while it's manipulating as well, or it has like this paper towel task, or it's picking chips from a shelf. And we analyzed actually, we compared to two baselines in these real scenarios. One is just the baseline where we collect a lot of data from different initial start position. Of course, that requires you to collect a lot of data, and on a mobile robot, that's extra painful. And then we have a baseline that is basically a person who doesn't know how the policy works or hasn't trained this policy, and just drives up to a place that is intuitively making sense if the robot should be picking up the paper towel, for example. But they don't know what is in distribution for this policy, right? And so you can see here a breakdown of where navigation fails, just drives up to the wrong place, or where the grasping actually fails, or where it actually is in distribution. And here on the very right, you see the overall success rate. And so you see, even for the person who has an intuitive understanding of where the robot should roughly be to pick up the paper towel, they still fail because they don't take the manipulation policy into account. So here's some here's some more rollouts of these tasks that show what this method can do. And here you see a baseline that is just trained on a bunch of starting position, and typically it gets confused in this funny way. And here's actually a person. Oops, let me go back to this. Here's actually a person driving up to this chip bag. So this person knows, oh, the robot is supposed to grasp the chip bag, probably the green one. But again, it just drives up to what should roughly be okay. But again, the robot can't actually do it because it's not in distribution with the policy. Here are a few more successes and failures as well. And let me just go to a few more interesting results where we do generalization to unseen scene layouts of our methods, and also include actually the height of the object as well, and optimize over that as well. And here we finally have more like a long horizon task where the robot is tasked to basically close all the drawers in the kitchen and has to basically chain this task together. And here's a visualization of how this actually looks like. So we have a generalization in the whole grocery store, and you see our algorithm in action. It basically starts to converge this particular base pose to a good position that is in distribution for the manipulation policy that actually does this poor tomato task. Okay, so this was the MobiPy framework. I hope you'll find it useful, also maybe to think about how you would approach this task of putting a manipulation policy on a mobile robot. We proposed the methods as well. Here are a few limitations. For example, our method doesn't handle dynamic scene changes. We also didn't look at multitask policies, but this is just the beginning. So thank you very much for your attention.